Welcome back. So we continue our discussion on now, or rather, move our discussion to so momentum theory calculation. So what we have talked so far, we have looked at the different, brief history of the horizontal axis wind turbine, and more importantly, we have discussed about the different components of the horizontal axis wind turbine, and then we look at different or rather discussed about those different components, their importance and things like that. Now we want to look at the aerodynamics of this horizontal axis wind turbine, and in that context, the most important thing is that we have to see how you calculate this thrust force, essentially the lift force, all the moments which are associated with that. Okay, so we'll continue on that from. So what we are going to look at is the momentum theory. Okay, so we'll discuss about the momentum theory, or somewhere you can think about it's called actuator disk model, and from there we'll establish the Bethe limit. So this we have, so this is essentially the CP max. That's the power coefficient, maximum power coefficient that a particular turbine can have. Earlier we have talked about it, but now we are going to see how that is going to arrive, okay, or achieve. So we start with this. Let's say the schematic. So this see the turbine which is kept there and at different location. So what happens is, if we extend this and try to draw this is going in the direction of X, and let's say if you have this velocity profile, then you have this U naught here, and then so one can think about this will go like this, it will come like that, and okay, so let's say this could be U naught, this is U1, U2, U3. So that's how, and around that turbine, we have drawn this steam tube or steam lines. So obviously, this turbine is modeled as an actuated disk. So what you can see, the wind is slower approaching at and after the wind turbine. Okay, so this steam tube, which is drawn here, this is defined as a tube whose boundaries are parallel to the fluid velocity of the wind passing through the turbine. This is what we have drawn here. So let's say if the P air, which is power in the air, that that would flow through the actuator disk. If the actuator disk is not there, then this could be half rho A U naught cube, which is probably not achievable in reality, because there could be losses and other things. So at this point or reference zero position, this is the velocity that you have, and that much of wind energy power in the wind that is available. But this cannot be achieved in practical scenario. So shows the this graph or plot which shows the axial wind velocity, axial wind velocity, which slows down as it approaches the turbine. Okay, and is slowed down further as it passes through. Okay, so what we have, I mean, we can write that u of minus infinity is u naught, u of 0 is u1 equals to u2, and u of plus infinity is u3. Okay. So when you go further away in this side, then you have u naught. When it reaches here, which is essentially the location of the disk. So what we assume, we can assume there is no interaction of steam tube with outside. Okay, so that's what is there. So what we can do is that when you look at this, we can also look at the pressure situation. So let's say we plot with X. So this is P of X. So pressure goes on shooting up, comes down, then stays somewhere. So this is what happens. Okay. This is 1, 2, 3, again 0. So here P of 0 equals to P of minus infinity, and P1 is P of 0 minus, P2 equals to P of 0 plus, P3 equals to P infinity equals to P naught. So this is how this is your reference position, and this is how the X varies. So what it tells you is that the pressure is built up as the wind approaches the turbine and drops after passing the turbine. Okay. So that's what you have. So what you now we can find out the mass flow rate through turbine, which would be m dot rho a u1. So here rho is, assumed to be kind of assumed to be constant as flow is incompressible. So we are talking about that. So then we have thrust of turbine, that is force again wind. Okay. So that essentially difference in pressure in the over area. So we can write P2 minus P1. So this one, this one we mark it 2, question number 2. So equivalently, we can write, say the momentum, we can say not U0 minus U3. So this is our equation number 3. Now we get power extraction. So that is P thrust into U1. Or we can say change in, let's say, so this we can say equation 4. We can say this is equivalently change in kinetic energy. So then we write power m dot half u0 square minus u3 square. That is equation number 5. So let's say given u1 equals to u2, p3 equals to p0, and u0 p0, what we need to find out u1 u2 p1 p2. So these we need to find out. Okay. So the first equation that we have, P equals to A into P2 minus P1 equals to m dot U0 minus U0 minus U3. Okay. So that's what, and now using Bernoulli's equation without energy extraction, what we can write, we have P plus half rho U square equals to constant. This is again along a streamline, we can write that. So therefore, wind flowing through the disk, which is essentially along a streamline, but we can write P naught plus half rho U naught square equals to P1 plus half rho U1 square. That is 7. So now what we write after passing the disk, assuming energy loss at the disk, we have P2 plus half rho U2 square, P0 plus half rho U3 square. It's a Bernoulli's equation that we write along different points. So there's a reference point 1, 2, and 3. So what we do, you eliminate P1 and P3 from equation 6, 7, and 8. What you get, P1 equals to P0 plus half rho U0 square minus U1 square. This is 9. P2 equals to P0 plus half rho U3 square minus U1 square. 10. P1 equals to P1 minus P2 equals to half rho U0 square minus U3 square, which is 11. So you have this. Now with equation 6, what we write, A equal into first P2 minus P1. Okay. So that's essentially 12A. So we can write A half rho U0 minus U3, U0 plus U3, rho A U1, U0 minus U3. 12B. So that's half of U0 plus U3 equals to U1, which is 12C. So what happens is that basically if you look at this, so there is a drop, then is a drop. So this is U3, this is U1, this is U0. Okay. Now we introduce some kind of an induction factor. Induction factor of A, which belongs to 0 to half. Now what we got, induction factor is defined as U0 minus U1 by U0. Now using 12C, what we get, U1 equals to 1 minus A U0, and then what we get, U3 equals to 1 minus 2A U0. Okay. So this is what we get, U1 and U3 using induction factor. That's what you have. Now, what we can compute power and thrust as function of A. So our P is rho U1 A half of U0 square minus U3 square, which is 13A. So this is half of rho U0 cube 1 minus A 1 minus 1 minus 2A square 13B. That is half rho A cube 4A into 1 minus A square. So that is 13C. So this guy is essentially, if I look at the power coefficient, which is Cp, this is the rotor power divided by power in wind. So that means P by half rho A. So if I compare this, then what we have, this is essentially my CPA, the power coefficient. Similarly, we can write P, that is m dot U0 minus U3 put in A, rho U1A U0 minus U3 put in B. You can have half rho A square 1 minus 1 minus 2A. 14C half rho 4A into 1 minus A. 14D. So again, this is my CT of A, that is thrust coefficient. If we compare this power coefficient and thrust coefficient, so what you can have is that that Cp of A 1 by A Ct of A. So this is what you get. Okay. So one can have some power coefficient and the relationship between thrust coefficient. Okay. So what we can do, we can maximize power extraction. So if you plot this guy, let's say 0, then 0.2, 0.4, 0.6, 8, 1, and 1, 2, 3. So this is Cp of A. So you can have a like this, and a kind of an curve and then it goes like that. So you can have some barrier here beyond which the momentum theory is invalid, and that is because my Cp is 4a 1 minus a squared, so dCp of dA is 0, from which we get essentially a star, which is 1 by 3. So the thing which is maximum at 1 by 3, this is A. This is at A star 1 by 3. And so then obviously A star is the optimal induction factor. So at A star, Cp of A star is 2/3 square, 4 into 1/3, which is 16 by 27, that is 5/9. That's what well-known Bayes limit. So maximum power coefficient can be like that. Similarly, if you plot the so you could plot so this is at 0.6. So you will have it at that is Ct of A. Now Ct of A is 4a into 1 minus a. dCt by dA equals to 0, gives us A star equals to half. So this is at half. So Ct at A star is 4 half into half, which is 1. So this is 1. This is Ct max. Okay. So that's what you get, that these things. Obviously, this Bayes limit that you have, I mean, so this is the maximum theoretical possible rotor efficient, but in practice, the effect lead to decrease in maximum achievable power coefficients and all these things. Okay. So, but this is what the theoretical calculation gives you. So we'll continue this discussion in the next session.